For a rectangle with area 100 to have the smallest parameter, what dimension should it have? When dealing with a problem involved geometry, we should always draw a diagram. In this case, a simple rectangle will suffice. We draw a generic rectangle. The dimension of the rectangle is the length and the width. With the given information, we were told that the area of the rectangle is the length times the width, and it is 100. The objective here is to have the smallest parameter, and then we associate the length, the width, and the parameter. The formula for the parameter is twice the length plus twice the width. We're looking for the dimension of the rectangle, meaning we're looking for the length and the width, such that that length and that width will give us the smallest parameter. The first step is to identify the variable, the unknowns, and the unknowns in this case are the length L and the width W. So we have two unknowns here. The next step is to determine the objective equation. The objective equation is the equation that we are trying to optimize. In this case, the quantity that we try to optimize is the perimeter. In fact, we want to minimize the perimeter. But the equation for the perimeter is P equals 2L plus 2W. Smallest parameter is the problem of minimizing a quantity. Next, we need to identify the constraint. The constraint is the condition that we have to work with. In this case, we need to minimize the parameter while keeping the area, while maintaining the area length times width to be 100. So the equation for the constraint is L times W equals 100. And the objective equation is again P equal to L plus 2W. This equation has two unknowns, so we will use the constraint to isolate one of the variable. If we isolate L, then we have 100 divided by W. We then rewrite the objective equation. The objective equation is now P equal 2 times L, but L is 100 over W plus 2W. We simplify this to get 200 over W plus 2W. And then we solve the problem, whose objective is P equal 200 over W plus 2W, subject to the constraints that L times W equals 100. But again, we already used this constraint to rewrite the objective equation. Once we obtain the equation in one variable, we will differentiate it. The derivative of 200 over W is 200 times the derivative of 1 over W, which is negative 1 over W squared, plus the derivative of 2W is 2. And so this is minus 200 over W squared plus 2. Keep in mind that when we take the derivative of 1 over W, we rewrite this as W to the negative 1. And the derivative of W to the negative 1 with respect to W is negative 1W, and we lower the power by 1. That is how we get negative 1 over W squared. This derivative is undefined when W equals 0, because if W equals 0, then the derivative will be undefined where 0 is in the denominator. However, 0 is not even in the objective equation because the objective equation have W in the denominator, and so this is not a singular point. We also noted that we're dealing with the dimensions, so W, width, and L, the length, has to be positive. We then find any stationary point by taking derivative and set it equal to 0. The derivative is minus 200 over W squared plus 2 set equal to 0. The common denominator is W squared, or we multiply W squared to both sides of the equation to get negative 200 plus 2W squared equals 0. This will give us 2W squared equals positive 200, and so W squared equals 200 over 2, which is 100. W equals the square root of 100 equals 10. In this case, again, W has to be positive. If W equals 10, then the length was 100 over W. And so the length L is 100 over 10, which is also 10. And so the tentative answer, the possible answer, is now when the length is 10 and the width is 10. But how do we know that this combination, this stationary point, will minimize the perimeter? We can check by using the first derivative test. We see that when W equals 10, the derivative p prime, it was 200 over W squared with a negative plus 2. If we pick a number between 0 and 10, for example, if we pick 1, then we see that p prime equals negative 200 over 1 squared plus 2, which will make this interval negative. If we pick another number in the interval 10 to infinity, W equals 11, for example, then p prime is negative 200 over 11 squared plus 2. And negative 200 over 11 squared is less than 2, and so negative 200 plus 11 squared plus 2 will be positive. And so the derivative is positive in the second interval. What this means is that the graph of the parameter is decreasing up to 10 and then increasing, which means the parameter is the smallest when W equals 10. And so we confirm that the parameter is the smallest when the length is 10 and the width is 10.